let me go to the window and see the burrows looking, it was raining, and so I just thought I'll go out near the window and look at it. And this is what unfortunately I found. It was raining also a little bit, but this was the picture I took. You can see some Chinese letters very barely visible at long distance. But this is the light which I could see out of the window. It's all the light I could see because I was on the 17th floor of the hotel. And in that hotel room, I did a little experiment. Okay, now I want you to guess the experiment. And that experiment gave me this picture. I didn't do anything extraordinarily great, but I did a little experiment. And this picture came out. Now the first year students only, the quiz. What happened here? What experiment did I do to get this? What is this picture telling you? You are actually seeing something quite dramatic associated with the previous slide. See, that was the night. Okay, you look at this one, the brightest of the lot. And I did this and I got this. What did I do? Anyone? You were there in all my talks. Okay, anyway, what I did was, I just pulled the curtain which was put at the window. You know that China is very famous for making very nice lace. So there was a lace curtain. And in that lace there were very, very tiny holes, and these holes were repeated uniformly in all two directions. It provided me a great fit. And therefore light acted. The light, we had the diffraction because of that grating. And indeed, this kind of a grating will also issue a situation where you can actually find the distance at which the light source is from my hotel room if you measure these distances. Okay, if you measure these distances, which are at this point, you can also find out how far is this light is from my hotel room. That is a question which you should answer. Think about it. How you can actually find how far is this light source from the hotel window. Okay, and you will be surprised to see how it is so if you assume the light source to be sodium. I'm not going to make it white light, so you have a single wavelength. So take it as a sodium light, sodium vapor light, and you can find the distance. And you will be surprised that it's so easy to find the distance. Anyway, this is diffraction. So if light can show diffraction, X-rays, which are also in the form of light, can also show diffraction, and that was the next step. And which essentially told us this I have been mentioning, so I didn't show in the afternoon, so I thought I would show you this picture. This is essentially what we normally see. It's a loaf of bread, and this loaf of bread represents a unit cell. So the advantage of looking at a loaf of bread is that you can see it immediately, number one. And number two, this represents the three axes. Something happened. This is I switched it up. Thanks. Right. So you can say that this is the A-axis along the horizontal direction, the B-axis and the C-axis inverse. So whichever is. So you have a unit cell. So a unit cell in a crystal is also something very similar. And you can now take this unit cell and make these into slices. And these slices now will represent the so-called Miller indices planes, because if you can now consider this as 0, 0, 0 as the origin, and then we come up here, there is one unit along the A direction, so this becomes 1, 0, 0. If you want the 2, 0, 0 diffraction, what you have to do is to cut it exactly at the half point and remove the central slice. The central slice will represent 2, 0, 0, and then 1, 3, 0, 0 will be the 1/3 slice and 1/4 slice and so on. So we can now get all the Miller indices in that direction. We can also cut the slice of bread in any way we want, and then therefore we can cut it this way, we can get the 1, 1, 1 plane. And what is very interesting is once we have these planes, we can spread these planes on a platter like this. I'll tell you a secret about this slide later. So you spread it on a platter like this, and this is on a plate, and you see that the surface has some holes here and things like that. Imagine these were the pieces of cashew badam, all those things which are added if you make a special bread. I was mentioning in the afternoon. So if you make a special bread, you will have all these pieces sticking out together. And those will be your atoms associated with the planes. So when you send an X-ray beam, you will get X-ray diffraction from this plane following the Bragg's law. But what actually diffracts the X-rays is not this particular plane. The diffraction is coming from the plane. The reflection is coming from the plane. But what is diffracting is the contents of this plane, which are the cashew badam and other things will be now the pieces of the atoms which are associated with this plane. So there will be some planes in which there are no pieces of badam and things like that. And those planes will not give you enough intensity. They will give some intensity but not strong enough. So the stronger is the content of this particular slice, the more we will see. In fact, the secret about this slide is very interesting. I'm sure all about this. This is a picture of which I took not from a piece of slice of bread, but this is the first ever picture taken by our satellite, which is the Chandrayaan satellite. The first ever picture produced by our satellite of the surface of the moon. So it looks like a slice of bread, so I thought I would put this. It's also the first ever picture we took from our IISER launch. So things are all very similar around the world. So these probably are some of those lunar craters or whatever. It's a very interesting thought. Anyway, so this is what happens. So now we measure all these and then do the routine crystallography now against it. Now, this is the logic of the whole thing. Whatever is happening in that slide is shown in this picture, and this is the one which utilizes the Bragg's law. You see that if you look at these small black dots, those black dots are the ones which actually represent what we call as the reciprocal lattice points. And these points are nothing but the planes. The representation of the plane is in the form of a point, because now we represent the plane as though there is a normal which is coming out of the plane, and we terminate that normal at a distance which is 1 divided by the d-spacing of that particular plane. So suppose you take 1, 0, 0 plane, you have the d1, 0, 0, 0, you take 1 over d1, 0, 0, and then represent that distance in the form of a point, and that will be the reciprocal lattice point. So effectively it is a clear-cut representation of all these reciprocal lattice points. And these are the various reciprocal lattice points from which X-rays get reflected, as was conjectured by Bragg and Bragg. So you get this diffraction pattern, depending upon the 2D sin theta and lambda. So this is the hypothesis. You see what is very interesting about this. Somebody asked me this question in the afternoon, so I sort of searched this slide from my collection, sitting in Anshu's house and took it out. What is very interesting is that if you see this lattice point, there are no atoms associated with that lattice point. The atoms are in other places. The green atom and the orange atom, these two atoms are the ones which are actually participating in the scattering. So any intensity which is coming is from these two, but it appears as though the intensity is coming from this particular reciprocal lattice point. So when you do the diffraction experiment, the atoms can be anywhere around, but they do contribute depending upon the nature of the overlap with which the two waves interfere. So if the interference is constructive, you will get a strong reflection. If it is destructive, you will not get any reflection. If it is intermediate, you will get intermediate reflection. So as a result, you get the intensity distribution, and then you can analyze. This is the typical picture which I have taken from Lasker and Krugler's book, which probably is available in your library as well. This essentially tells you the logic of how you do X-ray diffraction. So if you take, for example, a microscope. In a microscope, you have the object, you send in an X-ray beam, which in this case you send visible light. It falls on the object, you have a detector, which is an objective lens, we get an image of the object. This image now is passed through an eyepiece where we enlarge the image, and we get the enlarged image of this particular object. That is how a microscope works. X-ray diffraction is also a microscope, except that we do not have lens systems to get the diffraction pattern only to be analyzed. So what we do here is X-rays are sent to the object, which is a crystal. The crystal gives rise to all selective diffraction spots following the Braggs condition. So we have this diffraction geometry. And this diffraction, when analyzed, since the book is a very old book, you see there is a photographic film here. Nowadays we will use some super duper CCD detectors and so on. I will talk about that as to see what is available in present and what is there for the future. So in the case of the photographic film, in those days you needed this fellow, the crystallographer, who also assisted you to do this, what we call as the Fourier synthesis. With the use of a computer, it was possible to solve crystal structures. And it now so happens that this fellow, as I mentioned already, is a dispensable character. You need only that. Because he has already done whatever is to be done for this. So that this fellow now supersedes. And it all depends upon how fast this works, that your structure determination proceeds. So in principle, you can determine a normal, well-formed organic structure of about 20 atoms, 25 atoms, in a matter of 2 hours. And that's the state at which we have reached with X-ray diffraction. Anyway, what resulted with all this, with the discovery of X-rays, and particularly X-ray diffraction, this heralded a special new event in history of science. It's all very big words I put there. So X-ray crystallography was born with 2 Nobel Prizes. The first one to von Laue, and then to the father and son. What is very interesting is both of them did the same thing. It's nothing that somebody did very different from the other. What Laue found out in his own way was explained better and proved through an experiment by Brian. So you see the importance of a discovery of this kind, because you can determine structures with ease. In fact, the ease is very easy word to say, because over 1 million structures have been determined since then. Small, medium-sized, large proteins, thousands and thousands of protein structures are determined every year now. So it's something unimaginable. I think million is a very, I think it should be several million. And these structures have put enormous inputs, as you all know, to physics, chemistry, and mathematics. So this is the past. So you can always say a very nice past history, like we do in our country. We did that, we did that. We had so much of gold in our country. What the hell, how does it matter to us now? But we say we still have so much of gold. If we want to collect all the gold in the world, it is in India and nowhere else. And Fort Knox is nothing. All these things we talk. We only talk. So that's the past. Everything happened. Nobel Prizes were given. Discovery was made. It has paved the way for a large number of structures. What else has it done? We have to see what is it that is going to do. So in a typical X-ray diffraction experiment, you grow single crystals, you put it on this machine which is rotating. I don't have to even do that, it does it automatically. And then you get this, the reciprocal lattice reflections, and you get the crystal structure. Now what you get here is not just the crystal structure, you will also get the molecular structure. What you also get along with the molecular structure is the nature of intermolecular interactions. In fact, we can analyze the intermolecular interactions that are associated with it, and we can therefore look at what is important in terms of energy, what is the interaction which gives the least energy, what is the interaction which gives the maximum energy, and so on. And as a result, effectively, we can evaluate the energies that are associated with these. We can also look at situations where we can have intermolecular interactions differently. The same molecule having different intermolecular interactions, giving rise to the phenomena of polymorphism, which is now become a part and parcel of any drug design and drug activity. So there's a large number of drug industries which queue up to find out whether a given material can be made into a polymer. I think Anshu has done some work recently on generating polymorphs. So the generation of polymorphs is becoming, you don't polymorphs, I'm sorry, it's called Professor Anshu and Roy Chowdhury. Sorry, I shouldn't be using Anshu. I keep forgetting. I still think he's a small boy who came into my lab and he was trying to do what he wants to do. And in fact, I keep telling him that I've been selected. Because it so happened I was away somewhere. Where was I? Somewhere. I was in Glasgow. So I was out of the country, and my good friends, Ram Sesha and company, whom some of you might have met, Shukla, Ramsesha, all these are very, in Sanskrit we call them as Hitashatrus. You know what it means. So they selected Anshu. And I was a little concerned about this young boy who is talking very loud, but he was not very comfortable. So my first job was to make him comfortable. So once he became comfortable, he flourished. And he is now, of course, here. I don't want to talk about him now. He is still the present, definitely not the past. And I think he has some amount of future left. So I will talk about him now. But anyway, these are the situations where crystal structures will aid us to understand the molecular structure in a different way. We can make different kinds of molecules, make the molecule offer whatever it wants to offer. And this is where spectroscopy hand in hand with crystal structures will be of enormous use. Spectroscopists know how to handle these molecules. They handle them so very well across the electromagnetic radiation range that they can have different kinds of probes and evaluate these. And the parallel contributions which can come from crystallography is now presently one of the achievements in crystallography. And we can actually look at what happens to an atom when it becomes a part of a molecule, and what happens to a molecule when it is put in a crystal lattice at an enormously more detail, because what we plot here from an X-ray diffraction experiment is the electron density. So we can look at electron densities involved in bonds, involved in hydrogen bonds, involved in halogen bonds, and all kinds of many weak interactions. We can even draw a thin line between van der Waals interactions and weak hydrogen bonds. So these are some of the achievements which came through. But what we should always remember is the achievements which came in biology all of a sudden. In fact, biology made the maximum number of strides. In fact, the modern molecular biology was essentially born because of crystallography.